Let's explore the profound mysteries of the universe in a way that might change how you see everything. You've likely looked up at the night sky, seeing those little specks of light, and felt small. It's easy to think of the universe as this enormous, vast void that seems to serve no purpose, just endless space with no meaning. But what if I told you that space, as we understand it, might not even exist the way we think it does? What if everything you've been taught about distance, time, and the cosmos is only a tiny piece of the bigger, mind-blowing picture? Buckle up, because we're about to unravel a concept that will make you question everything you know about the universe. You may be sitting here, thinking about the distances in space. You know, the Andromeda Galaxy is 2.5 million light-years away. You've heard that light takes billions of years to travel across space. But here's the kicker. What if all these measurements you've used to quantify space, to measure distances between stars, planets, and galaxies are actually wrong? What if distance itself is not as simple as it seems? What if, at the deepest level of physics, distance doesn't even exist? What I'm about to explain will forever shatter your understanding of space and force you to rethink everything you know about the universe. To get there, let's start with something that's basic but often misunderstood: the speed of light. When we talk about the Andromeda Galaxy being 2.5 million light-years away, we're really talking about a time measurement, not a distance measurement. A light-year is defined as the distance light travels in 1 year. So when we say something is 2.5 million light-years away, we're talking about how long it takes light to reach us from there. But there's a catch. You're not measuring where Andromeda is right now. You're measuring where it was 2.5 million years ago, because the light that we see from it today left the galaxy millions of years ago. While the light was traveling, the galaxy was moving. The distance you measure is the distance to Andromeda, where it was, not where it is today. And here's the real twist. Space itself is expanding. While the light was traveling through the cosmos, the universe was expanding, making the current distance to Andromeda actually much greater than the distance that light traveled to reach us. So, when we think about cosmic distances, we're dealing with multiple versions of distance: the distance light traveled, the distance at the time the light was emitted, and the actual distance considering the expansion of the universe. These are three very different numbers, and none of them can be considered more real than the others. Depending on the reference frame you're using, the distance to Andromeda might not be the same from one observer to another. Distance in space is not a simple, fixed fact. It's all relative. The concept of a fixed, absolute distance is already being questioned. And it doesn't stop there. The idea of distance breaks down even further with Einstein's theory of special relativity. Einstein, in 1905, revolutionized our understanding of space and time, showing us that distance is not only relative, but dependent on how fast you're moving. For instance, when you measure the length of an object moving at high speed, it appears to be shorter than it would if it were at rest. This is not because the object is physically compressed, but because space-time itself behaves differently depending on your motion. This phenomenon, called length contraction, means that the distance between 2 points in space changes depending on the speed at which you're moving. At 10% of the speed of light, an object shrinks slightly in the direction of motion. At 90% of light speed, it shrinks much more. At 99% of the speed of light, the object contracts to just 14% of its original size. If you were traveling at light speed, the length would shrink to 0. This means that distance, in a way, doesn't even exist as we understand it. It is completely dependent on the observer's frame of reference and speed. A spaceship traveling at high speed toward Andromeda would measure the distance to the galaxy differently than someone standing still on Earth. For the person on the spaceship, the distance would appear much smaller, depending on the speed at which they are traveling. But this idea of relative distance isn't just some theoretical abstraction. It's grounded in real-world physics. It shows us that distance is not an absolute fact, but something that changes depending on the speed of the observer. The real question is, how do we make sense of all this? How do we measure distances when they depend on everything from our reference frame to the speed at which we are moving? And that's where Einstein's theory of spacetime comes into play. Spacetime isn't two separate things, space and time. They are intertwined into a single four-dimensional fabric that can be warped by mass and energy. Think about a sheet of rubber. If you place a heavy ball in the center, it creates a dip, and objects around it will roll toward the dip. This is how mass bends space-time. The more massive an object, the more it warps space-time. This is the fundamental reason for gravity. Massive objects like the Earth create a dip in space-time, and we feel the effects of that dip as gravity pulling us toward the center of the Earth. But what happens when we look even deeper? What does space-time look like at the smallest levels, where quantum mechanics dominates? And how does this affect our understanding of distance, time, and the universe itself? These questions lead us into the next phase of understanding, the quantum level. But before we dive into that, let's first grasp the enormity of what we've already uncovered. Distance, as we think of it, is not what we imagine. The universe, with its vast emptiness, is not empty at all. It's filled with dynamic fields and ever-shifting geometries. Time and space are not separate. They are interconnected. Space doesn't just sit still. It stretches and warps. The very way we perceive distances, the way we think about the vastness of space, is entirely dependent on our reference point. There's no fixed, absolute distance, only relative perspectives. So, let's break it down. When we look at the night sky, we see a universe full of distant stars and galaxies. But what we're really seeing is just a snapshot of time, filtered through the lens of relativity and warped by our own human understanding. The truth is far stranger, and the distances we measure are not as simple as we think. The universe is an ever-changing dynamic structure, one that challenges our deepest intuitions. Now, let's dive even deeper into how our understanding of space and distance continues to unravel. When we think about how the universe works, we tend to look at the vast distances between stars and galaxies. We see the galaxies, like the Andromeda Galaxy, as points far away, and we measure their distance in light years. But the truth is, these measurements aren't as simple as they seem. Space and time are far more intricate than our minds can grasp. The distances we measure aren't as fixed or absolute as we think. They are constantly shifting, relative to the observer and the circumstances. If we go beyond our own planet and start to think about the universe on the cosmic scale, something extraordinary happens. We begin to realize that the universe is not a static stage with objects scattered across it. It is an ever-expanding dynamic entity. This expansion is not something we see directly, but it is happening right under our noses every single second. The fabric of space itself is stretching. If you imagine the universe as a balloon with galaxies on its surface, when the balloon inflates, the space between the galaxies increases. The galaxies aren't moving through space. They are being carried apart as space itself expands. This expansion of space, and the fact that the speed of light limits how quickly information can travel, changes how we understand the universe. When we look out at the night sky, we are not only looking at light coming from stars and galaxies, we are looking at a snapshot of the universe that has been warped by the expansion of space and by the passage of time. This means that even the distances we think are static, like the 2.5 million light-years to the Andromeda Galaxy, are affected by the ever-changing geometry of space-time. The further away something is, the more its distance is influenced by the expansion of the universe. This introduces the idea that the universe we observe is not the same as the universe as it is now. The light we see from distant galaxies has been traveling for billions of years, and the space it traveled through has expanded during that time. The expansion of space itself challenges our perception of distance. It isn't just about measuring how far light travels or how far galaxies are from each other. The space between galaxies is expanding, and that changes the very fabric of the universe. What we see as empty space is not empty at all. It is full of energy, full of activity, and full of potential. As the universe continues to expand, the distances between objects in space grow. And while that might seem like a vast empty void, it's not really empty at all. It's just that the space between things is constantly growing, and that changes the way we understand the vastness of the universe. And even though we think of space as an empty, void-like region, it's filled with these incredible fields that stretch and bend. It's not an empty void, as we often think. It's more like a fabric, woven together by the forces and energies that permeate it. These forces, like gravity and electromagnetism, act on objects within space and cause them to interact with one another. The curvature of space-time caused by massive objects bends the path of light and dictates how objects move in the universe. But this curvature doesn't just apply to massive objects like planets or stars, it also applies to space itself. Space itself is not a fixed, static entity. It is something that can stretch, bend, and curve. And this is what makes understanding the universe so complex and so fascinating. Now, let's step back and look at how this concept of distance and space has evolved throughout human history. The way we think about the universe today is not how it was thought of in the past. In ancient times, people believed that the Earth was the center of the universe. The idea of the cosmos being vast and filled with galaxies and stars was incomprehensible. The stars were just tiny points of light, far above us. And the idea that these distant objects were part of a much larger, expanding universe was completely foreign. Even after Galileo and Newton's revolutionary contributions, the universe was still thought of as a fixed, unchanging entity. But as we've learned more about the universe, especially in the last century, our understanding has completely shifted. Einstein's theory of general relativity and the concept of space-time changed everything. We now understand that space is not empty. It is a fabric that can be bent and warped by mass and energy. The speed of light is not just a measure of how fast light travels. It is the speed at which information can travel. The universe has limits, and the speed of light is one of those limits. This speed limit also applies to the expansion of space itself. As space stretches, it carries galaxies with it. The expansion of space is not just an abstract concept. It is an actual, measurable process that is occurring right now. So, when we look at the stars and galaxies, we are seeing a snapshot of the universe as it was billions of years ago. We are seeing light that has traveled across space, carrying information from a time long past. And that light, as it travels through space, is affected by the expanding fabric of the universe. The farther we look, the more we are seeing a universe that is constantly changing, constantly stretching, and constantly evolving. But this doesn't mean that the universe is meaningless or that our place in it is insignificant. It's just that the universe is far more complex and mysterious than we could have ever imagined. And as we continue to explore space, we'll only uncover more of its secrets, and our understanding of the cosmos will continue to evolve. So the next time you look up at the night sky, remember that the vastness you see is not empty or meaningless. It is a universe in constant motion, constantly stretching, bending, and evolving. The distances we measure are not as fixed as we once thought. They are influenced by the expansion of space, the curvature of space-time, and the passage of time itself. And as we continue to explore the cosmos, we will gain a deeper understanding of just how strange and wonderful our universe really is. The universe is not just a vast, empty space as we often perceive it. When you look up at the night sky, it may seem like there's nothing but darkness stretching endlessly in every direction. You might think that space is a colossal, pointless void, a seemingly meaningless expanse between the stars. But as you start to understand the true nature of space, you'll realize that nothing could be further from the truth. Space, in all its vastness, is a dynamic and ever-changing entity. What we perceive as emptiness is actually full of unseen forces, energy, and complexities that we are only beginning to understand. To start grasping this concept, let's dive into how we view space and distance. You might think of the distances between stars and galaxies as absolute measurements, but the truth is, these measurements are far from simple. Space and time, once thought to be independent entities, are actually intricately tied together in a relationship we call space-time. And this is where the problem lies. Our common sense is based on the world we experience at a human scale. The universe, however, does not adhere to the same rules. The universe is not a static, empty box filled with objects. It is a living, breathing entity that is constantly stretching and evolving. Imagine you're sitting down right now, and you hold your arm out in front of you. You feel a force pulling your arm down, right? Your instinct tells you this is gravity, a force reaching out from the earth, pulling your arm toward the ground. But here's the thing. What you're actually feeling isn't gravity pulling your arm down. It's your muscles fighting against the natural geometry of the universe. You feel weight not because gravity is pulling you, but because your muscles are resisting that pull. In fact, if you were to jump off a diving board, you'd experience weightlessness. That's because you're not resisting gravity when you're falling. Your experience of weight is based entirely on the interaction between your body and the surfaces around you. This idea breaks the conventional understanding of gravity that we are used to, and it helps explain why space isn't as simple as we think. Our understanding of the universe started to shift with the work of early scientists like Galileo. Galileo didn't have advanced telescopes or the technology we have today. He used simple tools to study motion, rolling balls down ramps and measuring how far they traveled. He made an astounding observation. Objects in motion don't need to be constantly pushed to keep moving. This was a huge breakthrough, as it contradicted everything people had believed about motion. If something was moving, it needed a constant push to keep it moving. But Galileo showed that things just kept moving on their own. This idea would lay the foundation for future discoveries. Then came Isaac Newton, who extended Galileo's work by making a groundbreaking realization. Newton looked up at the moon and noticed that the same force that made an apple fall to the ground was also pulling the moon toward the Earth. The moon wasn't falling straight down. Instead, it was moving sideways so fast that it kept missing the Earth. This observation led to the development of Newton's laws of motion, and for a time the universe was viewed as a giant clockwork. Space was seen as a rigid, unchanging backdrop against which objects moved. The stars, planets, and even the moon were all part of this grand clockwork, following predictable paths. However, there was a flaw in this understanding. Newton couldn't explain how the Earth was able to pull the moon through the vast emptiness of space. How did the Earth's gravity reach out across millions of miles to affect the moon? There was no rope, no physical connection between them. This question bothered Newton, and it set the stage for future discoveries that would shatter the rigid, fixed concept of space that he had envisioned. The solution came from Michael Faraday, a man who didn't rely on advanced mathematics but instead used his intuition and observations. Faraday discovered something revolutionary. He realized that space is not empty. It is filled with invisible fields. He demonstrated this by experimenting with magnets and coils of wire. When he moved a magnet near a wire, the wire would react, but there was no physical connection between them. Faraday proposed that space was filled with these invisible fields, and when a magnet moved, it would affect the surrounding space, sending ripples through it. These ripples were the forces that caused objects to move. Faraday's insight set the stage for Einstein's work, where he expanded upon these concepts. Einstein's theory of relativity took Faraday's ideas even further, showing that space and time are not independent. Instead, they are woven together into a fabric known as space-time. Einstein's famous thought experiment about a sausage illustrates this idea. When you slice a sausage, the slice you get depends on how you cut it. If you slice it straight across, you get a circular cross-section. But if you slice it at an angle, you get an oval cross-section. This analogy helps explain space-time. Depending on your reference frame, the way you experience space and time will differ. The faster you move through space, the more time and space are warped for you. This concept is crucial in understanding why the universe looks the way it does. The vast distances we perceive between galaxies and stars are not fixed. They are affected by the geometry of space-time. The expansion of the universe itself also plays a role in this. As space stretches, galaxies are carried further apart, and the light that travels from them takes longer to reach us. This makes the universe appear far larger than it actually is. When we look at the night sky, we are not only seeing distant stars, we are looking at the universe as it was billions of years ago. And as we continue to study the cosmos, we uncover new layers of complexity and wonder. So, when you gaze at the night sky and feel small, remember that you are connected to the universe in ways you may not even fully understand. The vastness of space is not meaningless. It is the result of billions of years of cosmic evolution. Every star, every galaxy, every tiny speck of light is part of a grand design that has unfolded over immense stretches of time. And as we continue to explore and understand the universe, we begin to see that the universe is not a fixed, empty stage. It is a living, breathing entity, constantly expanding and evolving. To understand space fully, we have to let go of our human-centered perspective and embrace the larger cosmic view. The universe is not static, it is dynamic and always changing. The distances we measure are not fixed, and the way we experience space and time depends on our position and motion in the universe. The more we learn about the cosmos, the more we realize that the vast emptiness we perceive is not an accident or a waste of space. It is the result of time, energy, and cosmic forces working together to create the world we know today.